Okay, well, thank you. First of all, let me say that I first experienced, at least in the literature, Cyrano when I started to do my graduate research in 1962. There weren't very many books on many body theory. In fact, there weren't any. There was just Thoules's book in nuclear physics. But there were a few lecture notes, and this is one that I found on my desk the other day when I had to move to a new office, from Cyrano in 1961. His work was part of, influenced my research. This is my second paper, the first one from after my PhD. And you'll see that I have a reference to Dominici here, and I thank him here. So the second thing I'd like to mention is, of course, more recently he wrote this book on random fields and spin glasses, and so I thought that it would be appropriate to talk about spin glasses and random fields. In this case, in displacive relaxor ferromagnets, which I learned about more recently. Just a minute, this is... Okay, so this is what it's supposed to be. I'm not going to tell you that because I don't have any time now. So firstly, what are displacive ferroelectrics? I suspect mostly you don't know. They're ionic crystals, typically ionic crystals such as this one, barium titanate, and they exhibit structural phase transitions from a higher temperature pyroelectric phase to a lower temperature ferroelectric phase. The reason for this is that the ions displace in opposite directions. Some are charged, so they make dipoles, and those, I'm going to argue, are like soft induced pseudospins. What we know already from substitutional alloys in other situations is that if you have frustrated interactions and sufficient quench disorder, then a periodically ordered system will transform into a spin glass, or can transpose into a glass. Corresponding thing here in ferroelectrics is that a periodically ordered ferroelectric transformed into something that in the field are called relaxors, and I will argue that those are pseudo-spin glasses. I might also mention that with an appropriate alloying of these ionic crystals, you can also get random fields, and you can get them easily. As you know, they're pretty difficult to get in magnetic systems. First of all, just to show you something about how these things look similar, these are AC susceptibilities. As you change the frequency, you have a susceptibility has a peak, and that peak is dependent upon the frequency. This is the one many of us know and love, a case of a spin glass, platinum manganese in this case, 1983. As you know, the interest in spin glasses really started in the early 1970s. This is a figure from 1961 in the field of these ferroelectrics. And again, this is the thing that was called a relaxor. It looks to me very much like that. This is yet another one that looks very similar. This is another relaxor ferroelectric system. The difference between them is that this classic one is heterovalent in that it's got an alloy character in which these two things have different valencies. In this case, they're both the same valency, so there's no charge disorder there. And I'll point out to you that this is a situation where effectively there are random fields. This is one where effectively there are no random fields. Of course, there are no fields in this one, and they all look very similar. So it's tempting to think there might be a connection. Typical kind of spin glass theory that you find in the book by Cyrano and Irena is a Hamiltonian with soft spins like this. And normally in this kind of language, when thinking really of Ising spins, you've heard all the talks have been on Ising spins, that corresponds to this kind of situation where R is negative, U is positive, and in the limit when R goes to infinity, U goes to infinity, and the ratio goes to a constant, gives you the Ising system. So the local Hamiltonian has two dips here, and these correspond to the two Ising cases. In the case of the displacive ferroelectrics, the variables are the displacement rather than the field. That's the field. Again, there's a term which either favors or disfavors moving away from the equilibrium position. There's an interaction, which partly comes because if they displace, they're ionic, and then their ionic charge to interact through Coulomb forces at long distance and regular quantum mechanical forces at shorter distances, maybe random some fields, and there's some global strain terms which I won't discuss further. So U is the displacement in this case, and the field in that case. In these cases, however, take kappa, that's the language that tends to be used, the analog of R up there, is typically small and or usually positive, whereas here is negative. Lambda, of course, is positive so as to bound the problem. Kappa positive means there's no preferred displacement without any interaction, so they look like that. However, if the interaction can bootstrap a divergence and replace that effectively by that in the case of the interacting systems. So they're soft, like soft magnets. A couple of classic pure systems are barium titanate and barium zirconate. They're actually so the Hamiltonian is just the one that I talked to you about before. They're very similar to one another in that they're titanium and zirconium both have the same charges, so therefore they'll obviously have the same Coulomb interactions, but they differ in the values of this quantity kappa. In titanium, kappa is close to 0, and it's quite easy then for the system to bootstrap ferroelectricity through the interaction terms beneath the critical temperature. For zirconium, on the other hand, this thing is too positive for it to be able, the interactions to be able to overcome the local displacement forces. So this one orders, the one with titanium orders, the one with zirconium doesn't. But of course, we're usually interested in alloys. So first, let me start by discussing an alloy in which you have a mixture of these two, zirconium and titanium. And the zirconium displacements are essentially negligible because the zirconate doesn't order. So effectively what you have is an alloy where the only displaceable ions are on the T sites, which is rather like in the case of an ordinary spin glass where some sites have got magnetic atoms and some have non-magnetic atoms. The interactions are frustrated and long-range, dipolar. The average is ferroelectric because we know that when they're pure, the titanate will become ferroelectric. So they're very similar then in concept to a diluted experimental spin glass, but with induced moment soft spins. So what would we expect for a phase diagram? Something like this. Just think about a hard spin glass where you'd expect a ferromagnet and then a spin glass that comes right down to the bottom here. It doesn't go that far because you have to buy yourself enough interaction energy in order to overcome the local displacement forces. Now, I anticipate that will not be any surprise to any of you who are spin glass people here. So this is the homovalent ferroelectric alloy, and this is the spin glass. I wouldn't think that's particularly surprising. They just happen to have hard spins and soft spins. But actually, that's much less clear to the ferroelectricians who don't really understand it, even after 70 years. But the one that was discovered in 1960s wasn't this homovalent or isovalent system. It was PMN, as it's called, which is lead, magnesium, niobium, oxygen. So that, however, I remind you, also shows those same kind of peaks, very much like PMN, like the platinum manganese, I mean. Let's try and see if we can model it. So Mg2 plus, normally these would have been 4 plus. It's like 4 plus and a charge of -2. Niobium 5 plus is like niobium 4 plus with a charge of +1. I'll call these things star to indicate some fictitious material which behave very much like the ones without a star, except the charges. All the other properties are the same. Now we know that the ionic radius of magnesium is almost exactly the same as that of zirconium. Niobium is almost the same as titanium. And so we might expect similar things for the kappas, the displacement forces. And hence, if we ignore the extra charges and the difference between barium and lead, one might expect that P, M star, N star, which means using these things instead of these ones, would behave like the first one that I talked about, which is abbreviated to BZT, barium zirconium titanate, and would have a relaxor phase. In fact, however, this material does not have a relaxor phase, and so it's likely that this other thing wouldn't. The reason why I think about this is that my first thinking on this particular system was that that would behave like BZT and would consequently have a relaxor phase. It doesn't, and the reason is almost certainly because lead is a much softer material than barium. The kappa values are very different, and the effective interaction in this one is actually ferroelectric, more ferroelectric than in BZT, and overwhelms the pseudo spring glass wherever the interaction is strong enough to bootstrap displacement. So we need more than looking at this thing that looks very much like the isovalent one, the one in which, in the spin glass language, you would have exchange disorder rather than random fields. And the answer, where does it come from, is that there are these extra charges which I've not been considering just in the last few notes. So what do these extra charges do? They give rise to random fields, as would magnetic charges if they existed. Hence it appears to me that the relaxor behavior of PMN requires random field terms. Remember, I've told you it looks like a spin glass, it looks like the other things, and we know from much of the history of spin glasses that people believe that the magnetic fields kill spin glasses, not produce them. So it has potential implications for the debate on the effects of fields on spin glasses. It also has some implications for the random field problem when you go beyond the situation of just ferromagnetic Ising models. And I would speculate that if you have a long-range, frustrated system with random fields, you might get something that looks very much like spin glass. These are actually some recent simulations by people in the ferroelectric field who don't use all the fancy stuff that the spin glass ones do, using, it's a model PMN in which the two materials, manganese and niobium, are assumed to have the same but average values of these local parameters, kappa and lambda. The consequence of that is that any disorder in them is only on their charges, not in their exchange interactions. This is what this group find if they look at the susceptibility, including the random field terms. It has a peak around the point where PMN has one. On the other hand, if they exclude those random field terms, it has a much sharper, higher peak, these are different scales, at the temperature of the ferroelectric, which is suggestive that the random fields can suppress this ferroelectricity and yield a glass-like peak in a system with these freshly frustrated interactions with ferromagnetic means. So I think there's some messages here for us to think about. These are the, oh, I'm sorry, I'm on the other computer. This is a much fancier kind of simulation of people in the spin glass area. It's done on lithium, holmium, yttrium fluoride, which is another long-range dipolar interaction system, and trying to see the effect of magnetic fields in an Ising system. And they find indeed that the ferromagnet goes to something else, which they call quasi-spin glass. There's definitely a reasonably kosher transition along here. What sort of transition there is over there is slightly open. So there's some puzzles here for people in our field to think about. Sorry. Another interesting concept that comes out of people's work on relaxor systems is the idea of polar nanoregions. Their experiments show that beneath some temperature TB, which is higher than the one at that peak, there's experimental evidence and simulational evidence for clustering. They call them polar nanoregions. What about the theoretical understanding of them? And I will argue that it's localization through disorder. And you can again relate it to something that we all know about. This is a mean field theory. This is just doing that same problem, but looking at it in mean field theory for the average value expected for the displacement. And kappa T decreases as a function of temperature. Now, there are always solutions with u equals 0, but the interest is in one which are not 0. If you compare it with the classic Anderson equation here, and identify the coefficients. Then you would identify E with minus lambda times U squared. U squared is always positive. That's a negative sign, that's positive. So you'll only get a solution to this one, other than U equals 0, if E, the solution to this problem, has E equal E negative. So finite U solutions to the first one, only if there are negative energy solutions to the second one. So what's that got to do with anything? Well, let's just suppose this is the density of states of the Schrödinger equation that I showed you. It's centered at a position which phenomenologically you would expect to reduce with temperature. What you can see is that if at the moment as I've drawn it, there are no negative energy solutions, so there are no U's. It's a paramagnet, a ferroelectric. However, as you reduce the temperature, that whole curve moves along until this edge crosses there. Then you would get a solution, and that would correspond in the physical-mechanical situation to a phase transition to order. However, we're actually discussing disordered systems, not ordered systems, so the random K. Therefore, we're going to look at density of states of systems with random disorder. What we know is the band edges are typically localized. So what happens as this whole thing moves along? First of all, that one crosses the origin, and you get solutions, but those solutions are localized. To have a phase transition, you need to have macroscopic solutions, not localized solutions. So this one, when that one crosses the origin, you start to get the polar nanoregions. When this one crosses the origin, you start to get the phase transitions and the peaks and things that I talked about. Of course, it needs a lot more fancy work, this. So you therefore think, but perhaps the extended phase diagram, if I might call it, is the one I had before, but then some dotted lines which are kind of more of a kind of crossover where these other things that are not truly phase transitions start to occur. This is roughly where you'd start to get them, and this is supposed to represent where you'd start to see them. But experimentally, the curves are not that unlike it, but these are more than 10 years old. So, in conclusion, I would say that ferroelectrics appear to be related to and potentially understandable in terms of ideas from spin glass theory. They also raise questions which are not usually addressed in spin glass theory. They have what you might call itinerant moments. They're somewhat analogous to the situation in itinerant spin glasses, the Stoner glass, as it was called by John Hertz in 1980 something. They also would occur in other models like the one I devised with Gatak, which is a 0 plus or minus 1 system, where without any interactions you'd favor the zeros. That would be an induced moment. And so, as I said, site dilution versus random fields plus spatial interaction frustration, all those things lead to similar susceptibility peaks, non-ergodicity, apparently driven by either of this or that, or of course the combination. And then the PNRs, as I said, are related to these percolation type of problems, which are rarely considered ever in the context of spin glasses. But I think that in trying to explain these relaxor ferroelectrics, it brings up a lot of questions about things that should occur in spin glasses when you start to look at more realistic ones rather than the Edwards-Anderson, the Ising version of the Edwards-Anderson. Edwards-Anderson did it for vector spins. And what exactly the origin is, whether there truly is a phase transition as opposed to some sort of sharp crossover, remains to be studied. Thank you.
Okay, thank you.